Good morning, one and all. Welcome to the session on modern software engineering. We've been looking into data mining concepts and understanding how knowledge is discovered from data, and we've seen some of the challenges in the data mining task. And we have also looked into the different approaches in data mining, including generalization, association rule mining, or correlation analysis, and then we moved on into classification. We have seen clustering, outlier analysis, time series analysis, and data mining on graph and network data. Then we started with data pre-processing, and we have looked into some methods for data cleaning and missing data. We have also had an overview of dimensionality reduction and feature subset selection. The next topic we will be dealing with is discretization, binarization, and transformation in data. Before we go into that, we will use some measures of similarity and dissimilarity. We will understand that, and then we will move on into discretization. Now, when you look at that, when we look at what data pre-processing is, we see uh, the data that we have in a data warehouse is aggregated, it's integrated, and it is cleaned and reduced. But it may not make sense all the time. The data that we use for input has to be presented properly. That presentation for proper data mining task is called as transformation. So can be done only with the help of understanding that you gain over the data. So we first have to know what data we have, and then you can perform some basic statistical description of the data. Then you can visualize data. Only after visualization we get to understand which are essential, and only that data we are going to pull and take out and use for data mining. So when we try to understand data, we have seen some of the basic ways in which data is organized earlier. Here we will look into some other methods, what data is used, how data mining can be used, and all that. Okay, now in this task, data is organized in different forms. The first one is the record form or the relational form. It's also called as a numerical data matrix. All of these are the same thing. This is the usual relational database model that we know of. For every document 1, 2, and 3, they have segregated team, coach, play, ball, score, etc., or the description or features about that data. So every database that we are using SQL or Oracle, all of them fall under the record or the relational database model. An image shown below is also a different form of relational database, where you have a transaction ID followed by a list of items. It need not be separated into columns, but still it is a relational model. So both these forms of data are called as records or relational models. And there is another type of data called as the graph or the network data. In the graph or the network data, all the data are clubbed into nodes. And from one data object to another data object, there is a link available. So World Wide Web can be identified as a graph data, or say social networking information can be identified as networking data or graph data. These are different forms in which data exists. And we can also have data in ordered form, or in the form of spatial data, image data, video data, multimedia, time series. These are all different forms in which data exists. Although data mining methods are not particularly available for some of these methods, for some it is available. The important characteristics of data, as we have seen already, are dimensionality, sparsity, resolution, and distribution. Now, these are every data is a value or a numerical or a quantitative or a qualitative value that describes a real world entity. So all the description or the features about a real world entity are called attributes, and all these attributes have values. So for any real world object, it is represented using attribute value pair. So for every attribute, you have its own value. That's how they are used. Uh, these attributes we have seen already can be either numeric or binary or nominal or ordinal. There are so many ways. We have already seen most of them. So I'm skipping through these slides. And we are going to see how we can measure statistical description about this data. When I say statistical description, it means I am trying to aggregate or summarize that data in a way that is more visualizable or more presentable or more interpretable. So, a business perspective, I should be able to see when I look at that data. That form of understanding the data should receive. So, that is through use of statistical descriptors. So, these statistical descriptors, you have learnt all of them earlier. The same we are going to use here also for basic statistical operation. We have seen mean, median, mode, arithmetic, weighted mean. All of these, I think, we dealt with in the last session. So, central tendency is measured in terms of mean, median, and mode. And when all of them are at the same central position, or when the mean, median, mode are equal, the data is called as symmetric data. We also looked into an example for this. Now, in real world, we will not have symmetric data. Our data is definitely going to be skewed. So when I have skewed data as input, my data mining may not work properly, or the outcome of data mining will also be skewed. So there's a skew that is expected inherently because of the skew in the input that I am giving. So it is necessary to remove the skew or the bias in data before we give it as input. So with that in mind, to remove this bias, or I can say, I'll give you the best example for the skew is, imagine you have collected attendance information of the whole class, and you are saying that the average class attendance is 80%. The average class attendance may be 80%, but out of 60 students, do almost all students have the same value around 80? Not possible. There are so many students whose attendance is above 90, and there are so many students whose attendance is below 40. But because I'm taking a numerical average, my mean value is coming around 80. But in reality, not many of the students will have an attendance which is close to 80. In that case, how do I handle? That is what I call as bias. Now, when that bias exists in data, I need to remove the bias, or I need to make sure that I have equal number of samples falling into 0 to 40% attendance, 40 to 80% attendance, 80 to 100% attendance. So that way I have to select my data properly so that there is no skew in the data. So this is an unskewed data where there is a positive skew. When there is a positive skew, it means that the mean is very much higher than the median and the mode. And you can see that there can also be a negative skew when the mean is less than the mode and the median value. Now, apart from measuring the central nature of data, we can also measure the dispersion in data, or how much there is a variance in data. Variance is measured by using standard deviation and variance. Those are the usual measures that we already know of. So not much about it. And there are other forms of analysis which are called histogram analysis. And in histogram analysis, you divide the data into frequency based bins and you see how much of data samples are available in each of the bins. Say for example, for the same attendance example, I'll say I divide all the students below 40%, 40 to 60%, 60 to 80%, 80 to 100%. Likewise, I divide them into bin and I make sure that there are equal number of samples in all the bins. That is called histogram analysis. So in every histogram, I just look into the distribution of data or the samples inside the bins. I can also use quantile plot or a quantile plot. We will look into these examples later when we come into classification. That time these will give a better understanding. And whenever there is a skew can also be caused because of correlated data. Whenever the data is correlated from when one attribute is correlated to another attribute, I can see that the data becomes skewed. So a scatter plot can show whether the data is correlated with each other or not. These are examples of uncorrelated data. Once I have got this basic idea of how my data is, then I can measure the similarity or dissimilarity in data. Measurement of similarity comes in the form of distance values. When I say how much these two data objects are similar, I have to see quantitatively. So if they are numeric values, quantitatively assessing the similarity is easier. You can just calculate the distance between the points. Whereas when you have other forms of data, the calculation or the way of finding or the similarity between them is difficult. So how do we handle that? Now, to identify this, we are having some methods or measures. The first one is used for nominal values. What are nominal values? Values that are having they have a constraint of taking from a particular set. So it can take 2 or 3 values from a particular set. So I have a predefined set out of which I can take some values. So in that case, you can take a contingency matrix for binary attributes, or it's also called as the Jacquard's coefficient. I think we saw this in the previous session. This is an example of Jacquard's measure. And we can also standardize these values according to their z-score. Z-score is a normal distribution z-score. We will look into the mathematical aspect of this when we come into Unit 4. So, the common measure of similarity and dissimilarity used for numerical values is the distance measure. The one that we use, the popular one, is called as the Euclidean distance, but Euclidean distance is a derivative of the Minkowski distance measure. The Minkowski distance measure, instead of using in the Euclidean measure, we usually use the square. So h value is set to 2. Instead of 2, if I have any other value, it can be called as the Minkowski distance measure. And in the Minkowski distance measure, if I put the h value as 2, I get the usual Euclidean measure, or I can even use the value of h as 1, and that is called as the Manhattan distance measure. And if I extend the value of h to infinity, it is called as the supremum distance or the L norm distance. So these measures are used for numerical attributes to find out the distance between two different values or data objects. So for an example, look at this example. So I have attribute 1 whose values are given and attribute 2. So for a data point x1, I have attribute value 1 as 1 and attribute value 2 as 2. And for x2 it is 3 and 5. x4 it is 2 and 0. x4 it is 4 and 5. So I've plotted those values, and when I try to calculate Manhattan distance, I use the formula given here. So I just calculate the distance between the corresponding x and y, x1, x2, and then y1, y2. So when you calculate the distance that way, this is the distance. A distance matrix is always symmetric in nature, so the diagonal elements are going to be 0, and it is going to be a reflection of whatever you have in the lower side of the matrix. The upper side is going to have the same value. So this is how you calculate the Manhattan distance. The same way you can also calculate Euclidean distance by raising the Minkowski to a value of h equal to 2. So okay. So this is how we identify similarity and dissimilarity in data. Once we receive this idea, we are now going to pass on into our next. So this is our summary. Let me conclude on things before we start with the next step. Once you have identified the type of data, you can find out the similarity between the data. If the level of similarity is high, or if the correlation level is high, then it means that the data is very similar. If the data is similar, if two attributes are very similar to each other, I can take only one of that attribute for further analysis. The other attribute can be eliminated, and then it can be removed from the data set before I apply data mining algorithms. Now, this helps me to see which of the attributes are highly essential. Once I see that these measures are essential for further processing, only that data I am going to take for data mining. So it is very equivalent to the selection process that we do in the knowledge discovery process. In the knowledge discovery process, we have seen that we started with data cleaning, we then moved on into integration of data. Then once the data is integrated, we select task specific data that can be given as input to data mining algorithms. Now, when I choose that task specific data, it is very essential that I understand the data first and then do the selection process. This way of statistical understanding, looking at the central tendency of data and identifying the dispersion in data, and also looking at the similarity measure and dissimilarity measure in data, gives me an overall idea about the data, or I get to have a deeper understanding about the data once I apply these statistical values. Once I analyze these statistical values, it gives me better understanding of my data. Once I have understood the basic nature of data, the selection of data for the data mining task becomes easier. So all these measures can be used, or they are practically in use today also. So these measures are used. Once these measures are calculated, I find out which of them are important. Once I understand which samples are important, then I take a note of those and then take them only for further processing. Now, in the KDD process, if you remember, After the selection of data, we directly start applying the data mining algorithms. However, in practice, it may not be possible. We might have to do some transformation in between. Data transformation is when one format of the data is changed into another format so that it increases the interpretability of data. Say, for example, if I calculate the attendance values, I look upon the attendance values, then I say an attendance of between 50 to 65 and 65 to 75, 75 and above. If I segregate my data samples according to that constraint, then it becomes easier for me to understand what decision I want to take with that. So what happens is I first distinguish my data properly, distribute them properly, then divide them into categories, and instead of using the value just like that, I can transform that value into average the attendance as low, medium or high. When I transform that numerical value into a qualitative value, becomes more interpretable. So that form or that is the process of converting a numerical value, that same numerical value into a qualitative variable to increase the interpretability of that data is called as data transformation. So we will be looking into some of the data transformation methods and binarization methods. Binarization means the process of identifying a yes or no out of or the outcome of a process in the data, that is called as binarization. So these aspects we will be dealing with in the next session. So for today's session, I'll close here. All of you stay home, stay safe. Thank you one and all.